Good morning. Today I am going to discuss some of the objective questions of the fracture. So let's see the first question. In metals, ductile to brittle transition occurs at. So in what temperature range basically ductile to brittle temperature transition occurs in a metal when the metal uh, go into undergo into the brittle fracture, okay, from ductile. So basically in the metal it is around the 0.1 to 0.2 of its melting point, but remember this melting point or the melting temperature must be in Kelvin scale. So this is the correct option, that is the C option, in which the metal can undergo ductile to brittle temperature in the temperature range of 0.1 to 0.2. Suppose we have temperature of 400 degrees centigrade, suppose, and we want to find the approximately dBdt temperature, then first you have to convert into Kelvin. So it will be 673 Kelvin, and now you have to find 0.1 and 0.2 of it, and you will easily get the value. So 0.1 is approx what? It is 67.3. Okay, so around 0.1 to 0.2 of this temperature will be the temperature range for dBdt. Okay, now let's do the second problem. In the ceramics, ductile to brittle transition temperature occurs. Ceramics are more brittle as compared to metals, so of course their dBdt temperature will be higher, and it is around 0.5 to 0.7 of its melting temperature. So in this the correct option is the option B. See the next question. Nil ductility temperature, that is the NDT, is the temperature at which the fracture is. So basically nil ductility temperature at NDT, the fracture initiates with essentially no prior plastic deformation. Okay, there is no plastic deformation, there is directly brittle fracture occurs or the cleavage fracture occurs, and we can say it is almost brittle fracture that will occur here, and the option will be B. And below NDT, the below nil ductility temperature, the the fracture is almost, the ductile fracture is almost negligible, that is 100% brittle is there. Now let's move to the fourth question. For satisfactory notch toughness, the manganese and carbon ratio in the steel should be, okay, as we know that the manganese decreases the dBdt temperature and carbon increases the dBdt temperature. Okay, so if you want the satisfactory notch toughness, then of course the manganese concentration should be higher. So it is around 3:1. All option it is higher, but the most suitable manganese concentration is 3:1. So manganese concentration should be 3 parts and the carbon should be 1 part. That is the 3:1 is the correct answer for this. Next, select the correct statement. Okay, the first is change in amount of carbon and manganese in a steel changes its dBdt significantly. That is true. If you increase 0.1% carbon, the dBdt temperature increases by 14 degrees centigrade. So you can see there is a huge increment in the dBdt when we increase even a minute amount of carbon. Okay, so that is true. Second, increase in carbon content in the steel increases its dBdt. Of course it increases, as we know that 0.1% increase in carbon increases the dBdt by 14 degrees centigrade. More carbon means it is more brittle. Its DBTT temperature is higher. Even at higher temperature, it can undergo brittle fracture. Increase in manganese contained in a steel decreases its DBTT. That is almost true. I have told you that when you increase the manganese, suppose you are increasing 0.1% manganese, the DBTT temperature decreases by 5 degrees centigrade. When you are increasing manganese by 0.1%, the DBTT temperature is decreased by 5 degrees centigrade. So we can say that when we add the manganese to the iron or the steel, then its ductility increases, or the low temperature application is more advisable by adding the manganese. Because the TBTT is lowered, it means it can undergo ductile fracture even at low temperature. Okay. The last one, the increase in molybdenum, phosphorus and oxygen in a steel increases DBTT. That is also true. Like carbon, molybdenum also increases the DBTT. Phosphorus is also detrimental for the ductility, or it can increase the brittle nature or the brittleness and increase the ductility. Oxygen or the oxide has very large impact in increasing the DBTT also. So all of these increase the TBTT. So in question number 5, in fact, all of the statements are correct. Okay. Now let's see the question number 6. Which steel has the highest ductile to brittle transition temperature? First is rimmed steel. A rimmed steel has high iron oxide content. That is very high iron oxide content, and if there is more oxygen or oxide, then DBTT of course will be very high. That it can show brittle nature even at even above the room temperature. Okay, so it is very brittle in nature. Now see, semi-killed steel has similarly low oxygen content, because in semi-killed steel we use silicon to deoxidize the oxygen, to remove the oxygen from the steel. So semi-killed steel has generally low oxygen content and its DBTT is lower. Low carbon steel, of course, it has low DBTT. It is ductile in nature. High strength low alloy steel, again it has very low ductile to brittle transition temperature. So the first option is the correct. The rimmed steel that contains a lot of iron oxide has the highest DBTT, and that is the worst for the low temperature application. Next, now let's see the semi-killed steel is deoxidized. Why? Again, we have discussed earlier that semi-killed steel is deoxidized by the use of what? Silicon. The silicon has a great affinity towards the oxygen, so silicon and oxygen can combine together to form SiO2, and it will get removed from the melt. Okay, so that is the silicon. The option C is correct in this case. Question number 8. Fully killed steel is deoxidized by. Rimmed steel has maximum oxygen content, then it comes semi-killed steel, and the fully killed steel has the lowest oxygen content, and in that case the deoxidation is done by the use of silicon as well as aluminum. So the option D is correct. So we can say aluminum can also react with oxygen to form alumina, Al2O3, that is the very high stable compound having very high thermal stability, and silica both will react to form SiO2. So you can say both can deoxidize the steel or can remove the oxygen out of the steel. So option D is the best one. Question number 9. Decrease in grain diameter. If you are refining the grain, then what is that? it increases or decreases the DBTT. When we refine the grain, the brittleness decreases, okay, at low temperature. When there is very fine grain, then at low temperature brittle fracture will not occur easily, because when we have fine grain, there are more number of grain boundary, or so the crack propagation is not easy for that, so brittle fracture will not occur easily. So we can say when we decrease the grain diameter, the DBTT decreases, so that is decreases. This is the answer for this. Move to the next one. And also we can say that the fine grain fine grain steel is better as compared to coarse grain steel for the low temperature applications. Now question 10. The low carbon steel exhibit two types of aging phenomena, okay, that increases transition temperature, that is quench aging and strain aging. They involve this and this respectively, okay. So as we know that low carbon steel has two types of aging, that if one is quench aging and other is strain aging. What happens in quench aging? Okay. So both of them increases the transition temperature or DBTT. Both of them makes the steel more brittle. Okay. And the main phenomena occurring in the quench aging is the carbide precipitation. When the carbide is precipitated along the grain boundary, so carbide is very brittle in nature, that is hard, and in carbide if it's hard, then there is more chances of what brittle fracture. So one is carbide precipitation, and another quench aging is done with the help of cold working. When you have cold worked material, when we do the cold working, okay, then it will have the strain aging. When we do the cold working, what will happen? The brittleness increases when we do the cold working. That is due to a strain aging. And when we do hot working, the ductility increases. So this is what carbide precipitation and cold working, that is the correct option in this case. So the option B is correct in this case. Move to the next. Blue brittleness, that is increases or decreases impact resistance in temperature range of this due to high rate of strain aging. Okay, so we know that this is about the blue brittleness. As the name suggests, this is the brittle nature that occurs in the steel in the temperature range of 232 to 370, and this is due to high rate of strain aging. So brittleness occur, it means DBTT has been increased. Okay, blue brittleness. Okay, DBTT has been increased. So the impact resistance, when there is brittle material, then it has very low value of impact resistance, or it can absorb the shock very low. Okay, it can absorb very low shock. So we can say it decreases the impact resistance of absorption of the shock due to increase in the brittleness, or you can say increase in the DBTT temperature. So that decreases is the correct option. The last one, let's see. Which microstructure in steel is the best combination of strength and impact resistance? Ferrite? No. Benite itself? No. Martensite? Benite is better than ferrite, but not the best. Martensite? No. Martensite is very hard and brittle. Tempered martensite, that is the true. Tempered martensite has the best combination of the strength as well as the ductility. That is the end of this lecture. Thank you.